To solve the problem mentioned in the previous video, a control system for process heat exchangers has been developed and is shown in the following P&ID schematic. In this arrangement, a portion of the cold stream is diverted to bypass the heat exchanger. We still have a temperature sensor on the outlet line of the hot stream, but the temperature loop that you can see here controls a valve on the bypass line and not on the outlet line of the cold stream. Here we still control the temperature of the target stream by throttling the non-target stream. However, by putting the control valve on the bypass stream rather than on the main stream, we effectively eliminate the flow fluctuation of the non-target stream. Whenever the control loop asks for a less cold stream, instead of decreasing the cold stream like what we did in the direct control system, we are bypassing a portion of flow around the heat exchanger. By using this trick, we satisfy the orders of the control loop, and at the same time, we don't change the total flow rate of the cold stream. This is a better arrangement when the cold stream is a process stream and has another responsibility downstream of this heat exchanger. However, the temperature of the cold stream is still changing, and if it is not tolerable, we cannot do anything for it in this heat exchanger. When the fluctuation in temperature may be too great for the equipment downstream, we can solve this by putting another heat exchanger in series with this one to control the temperature for the downstream equipment. The second heat exchanger must be a utility heat exchanger. Now we can have another variation of this arrangement as depicted in this next P&ID schematic. Here we have put control valves on both the discharge and bypass streams. We have already shown split range control of valves in a previous video. In order to maintain a constant flow rate when we have flow from both streams at the same time, we need to go with parallel control. Now we could substitute the two control valves with a single three-way valve as depicted here. However, keep in mind the disadvantage of using three-way valves is that they are not available in large sizes. They are also not suitable when they receive a stream with large temperature variations. This will cause different rates of expansion inside the valve, which inevitably leads to leakage. Finally, one very interesting variation of bypass control is shown in this last P&ID schematic. In this arrangement, we have a pressure differential controller PDC on the bypass line. If we have a situation where the pressure drop across the heat exchanger is large, most of the inlet flow will choose to go through the bypass line, where the pressure drop will be smaller. To avoid this, we can put in a PDC to control the pressure drop on the bypass line and thereby control the flow rate through that line. The situation where it is a big advantage to use a PDC on a bypass line is where you have a number of heat exchangers operating in parallel. If you didn't use a PDC, you would have to have a bypass line with a control valve for each and every heat exchanger. However, if you use a PDC, you only need to install one bypass line across the whole bank of parallel heat exchangers with one control valve.